So I would like to thank the organizer. It's a great honor and a great pleasure to be here to give this lecture. This is really an impressive group, seeing from the front here, showing many students. It's amazing. So I'm going to talk about statistics for zeros of data function over a function field or curve over finite field. But before that, I would like to start with the number field. And I would like to start by, in something I think the two biggest influence on the field would be the work of Karnak relating that to random matrix theory. And the recent work of Rudnick and his collaborator of treating function field in a way as you treat number field, which seems like a weird idea because they're working over function field. But it ended up recently on some results where people can use the function field results to actually prove something over the number field, which is surprising. So let's start with the general Karnak philosophy. Is that statistics for zeros of L function, and this is over number field, should match the corresponding statistics for eigenvalues of large random matrices. I guess that's a theme that now we're going to see in a lot of the lecture. We're looking at statistics, and Melanie was saying, in some cases, the statistics should match the statistics of random groups. Here, the statistics should match the statistic for eigenvalue of large random matrices. So when did it start? It starts with the word of Montgomery in 1974. Okay, so a statistics for zeros of L function, I should say, in families. I don't know if you see that or in families, so that's it. Like that. So what families he was looking at? Well, it's going to be a weird family because the family will be, in fact, all the zeros of the Riemann zeta function. So I'm going to suppose that T is real, which is to say I'm assuming the Riemann hypothesis. Did I do something? Okay. Why are you laughing at me? So? Is there something funny about it? Okay, I'm just going to assume for that, yeah. So I'm going to assume that T is real, and I want to look at all those zeros. So if you count the number of those zeros, so N of T are going to be the number of T between such that zeta of 1 half plus I T is equal to 0. So they're about T log T divided by 2 pi of those zeros. So I'm going to always normalize it so that everything fits together. I'm always going to normalize everything such that, you know, the mean spacing of the zero is 1. So I'm going to look with the 0, and I should have called them gamma. So gamma are going to be the 0, so zeta of 1 half, plus I gamma is equal to 0. And I'm going to call gamma tilde the normalized 0. Okay, so so this is my family. My families are the zeros of the Riemann zeta function. What is the statistic? The statistic would be the pair correlation. I need a statistics. So what is the pair correlation? So, okay, we're assuming that the zeros that, are on the real part. We want to know how correlated are they. So if you think of the zero, are they a random point on the line real part of S equals to 1 half? If you look at the first 1,000 zero, do they look like you just throw, okay, if you know the mean spacing, does it look like you just throw 1,000 random point with this mean spacing? That's what the pair correlation is going to tell you. So what is the pair correlation? 1 over the number of zeros. And then I look at pair of zeros, so gamma prime. And I took some test function f, and I look at the difference of the zeros that I normalize them. That's the pair correlation. So what did Montgomery prove? He proved that, so maybe let me know if it's okay. Okay. What's the theorem that Montgomery proved? He proved that the pair correlation, let me write it down, which is the sum over those pairs of zero of the difference of the normalized 0. He proved that this limit, when t goes to infinity, was given by, there was some very nice measure which would give you the pair correlation of those 0. I'm going to do the integral, and let me do that on the next line. I'm afraid I'm going to go out of screen. I'm going to do the integral of the function f of x, which is my test function. So times some kernel, and this is going to be sine square of phi of x divided by pi of x squared dx. Okay, I have to put some hypothesis. So if you look at the pair correlation, there's a natural measure which gives you the pair correlation. But there's an hypothesis for some test function, such that the support of the Fourier transform of f is limited. And actually, I have to say that I forgot to check what the limit means here. Okay, that's a number smaller than 1, but I forgot to check it as well. So for all test functions. Okay? So only for a special class of test function, you know that the pair correlation is given by this integral. Okay? So this seems like a theorem of, analytic number theory or measure theory. So I have a family, the zeros of the Riemann zeta function. I have a statistic, the pair correlation. So where's the random matrix theory? And of course, there's a story about that if you don't know, I have to tell you that Montgomery, when he finished his thesis, he was at the Institute at MIT. He met Freeman Dyson, and Freeman Dyson very nicely asked you, oh, what did you prove in your thesis? And he said, I proved that. He said, oh, so you proved that the zeros of the Riemann zeta function have the same pair correlation as random unitary matrices when n is large. So this is what he proved. So that's the statement. And what does it mean, this observation? Let me relate that to my random matrix theory. So take Un, which is a set of n by n unitary matrices. So those are matrices such as U dot U or U star. So this is the transpose conjugate is equal to the identity. Okay, so those have n eigenvalue, and I'm going to call lambda j of U. And because the matrix is unitary, the eigenvalue have absolute value 1, so I'm going to call the angle theta. And this is for j equal 1, 2. So, and now what I'm going to do is I'm going to look at the pair correlation. I didn't give a name to the pair correlation. Let me give the name C for correlation. My test function is going to be F. My matrix is going to be U. So it's going to be the sum over all the zeros. But of course, here there are finitely many zeros. And I'm not going to take the same zero. Some test function, I have to normalize my zeros. Now my zeros are the angles. So they're n angle, from 0 to 2 pi. So if I want to give them mean spacing 1, I have to multiply by n over 2 pi. So that's the pair correlation of n by n unitary matrices. And the pair correlation of n by n unitary matrices, so there's a theorem which tells that if I look at, n by n unitary matrices, that's a measure space. It comes with a natural measure, which is an R measure. So I can integrate this function with respect to the natural measure. And I can look at the n limit. If I look at the n limit when n goes to infinity, so this is the same thing. When you have the Riemann zeta function, I looked at, the pair correlation between zeros. I was summing over t zeros. I was taking the limit when t goes to infinity to get a statistic. You need an infinite amount of stuff. Each matrix has n zeros. So to get infinitely many zeros, I have to make the limit when the size of the matrix goes to infinity. My sum is now an integral because this is a measure space with this integral, as before the measure space was a natural measure. So, and this would be the integral between minus infinity and infinity of f of x, and of course I'm going to get the same kernel. I'm sorry, I'm left-handed, and it's probably a problem for writing that. So this is not Montgomery's theorem. This is Montgomery's theorem, giving you the pair correlation of the zeros of the Riemann zeta function. This is something which has only to do about random matrix theory. Okay? And this thing is called the scaling limit. This is people who do random matrix theory. Random matrix spaces are probability space. So people who do that are people who do probability. So they noticed that for the pair correlation, the scaling limit is like that for the unitary. So this is the same measure. So this is how it started, that people said, okay, the zeros of the Riemann zeta function seem to be distributed not like random points, but like eigenvalues of random matrices. By the way, I didn't have a chart, but eigenvalue of random matrices are really not random. In particular, there's a repulsion phenomenon. If I draw n random points on the circle, there would be some clusters. If I pick a matrix at random and I draw the eigenvalue, there will be a repulsion phenomenon. This is not the same distribution. and the zeros of the Riemann zeta function are distributed like that. So what are the evidence for Montgomery's conjecture?
Can you test the...
Yes. Oh, sorry. I kind of just threw it on the side. I forgot it was. Is it correct like that? No? Okay. I have to put it left or right? Left or right? Okay. My left. That way. Thank you very much. So what is the evidence for Montgomery's conjecture? Or maybe we could say, okay, I didn't tell you what Montgomery's conjecture was, but Montgomery's conjecture would be that this would hold for any test function f. That the statistics would be the same. Well, first of all, there's impressive numerical evidence by Oblisco. So it looks at zeros. I think the size of the zero is when t is equal to 10 to the 20. So of course, the conjecture is for the large n matrix, so you need to take t very big. So when t is like 10 to the 20, it took millions of zeros, and he checked it with the scaling density, and the fit is amazing. There's also a generalization to zeros of any automorphic representation on GLM, using Rudnick and Sarnak. And the pair correlation of those zeros, so you can take any automorphic function on GLM, and the pair correlation of those zeros will fit the pair correlation of matrix in the unitary group. There's a universality here, by the way, for the pair correlation. The statistic I will be interested in would be mostly the one-level density, and then there's no universality, in the sense that there would be a symmetry type attached to every family. For the pair correlation, you can take any automorphic form on GLM, you would get exactly the same scaling density. I don't know if you see it, but the 1 minus sine square of pi x over pi x squared, you would get exactly the same scaling density all the time. And of course, there's the fact that this was proven over function field. So over function field, what I mean by that, let me use this vocabulary first. As Jordan was saying, function field and number field, they go under the umbrella of global field. They have many, many, many similarities. But when we say it was proven over function field, you should think of function field as not as curves over finite field. That's the way you think about it. And when you think of them as curves over finite field, you have many tools. And also, as Jordan was saying, well, we say that Q is analogous to FQ of t, but there's many, many Q for which you have the FQ of t. So the function field things are proven at the Q limit. This is basically the linear distribution theorem, and I'm going to talk about that again. Okay, so this I'm mentioning that because this was the first example of the link between zeros of zeta function and random matrix theory. But actually the statistic that I want to study is not going to be the pair correlation. So another statistic. And the one I want to study would be the one-level density. Not too sure why it's called like that, but the one-level density is the study of the low-lying zeros. Just one of the reasons that you need family. The pair correlation is the study of all the zeros. So you have infinitely many zeros, of course, in the number field case. So you can take one L function. When you study the one-level density, you study the low-lying zero. So in order to get statistics, you need to get infinitely many of those low-lying zeros. So you need a family of L function. So let's look at that for family of L function of elliptic curve over Q. And also, that's going to be my first example. And my second example is going to be the family of L function attached to Dirichlet character. Well, in fact, quadratic Dirichlet character. Which is the L function in the field that Melanie was talking about. So I'm going to look at the LSE and the LS chi D, where D is the discriminant of the character or the discriminant of the field. That's the fundamental discriminant. So let me define the one-level density. So first let me define this function WF of E. Now I'm going to, maybe I should have define my elliptic. Let me write it here. Okay, let me write W f of E, where E is my elliptic curve. That's going to be the summation over all the zeros of and I'm going to have some test function. Again, I have to normalize my zero. So, and let me write that and explain after that. Okay. So I want to look at this function where gamma are the zeros of my elliptic curve over the critical strip. So let me put this on the side and write something that, so I'm writing my L function of my elliptic curve such that the center of the critical strip is at s equal 1. So if I write the completed L function, so this is going to be related to the functional equation related to point f to the point 2 minus f. Okay? So the center of the critical strip is at 1. Okay? So those are the zeros that we're studying. So now let me put it on the side. But in fact, yeah, I was to say let me put it on the side, but I don't have any more space on that sheet. So in fact, maybe I should normalize it to a center of the critical strip at 1/2, but I'm going to write it like that because I want to use the explicit formula on that format. Okay, so what's my WF of E? I hope you see it. So, and one now, okay, now I want to write it. Sorry. What I wanted to write is, I'm going to take f, which is a function in the Schwartz space, which is to say that my function is repeatedly decreasing. So what you should think about is that counts only the first year zero, because the function is repeatedly decreasing. That's a real function, which is repeatedly decreasing. And what about the normalization? Why by my normalization I have log of NE and not log of gamma E? Because now I'm going to run over a family. So what I'm interested in is that how many zeros every L function of my family has. And this is what I want to normalize. And how many zeros does any L function of my family has depends on the conductor. The conductor plays a role. Curves with large conductor don't have the same number of zeros as curves with small conductor. That's why my normalization includes the conductor of the curve. So are there any questions? I don't want to write all the details, but the details are on the notes. But if there's anything which is not clear or you think I'm overlooking. Okay, so that's what I'm doing. I'm looking at the low-lying zero with some test function. And now I'm going to look at the one-level density. It's going to be the average. So I'm going to give, it seems everybody has a different name for the average. I like this notation. So I have a family of elliptic curve, and I'm averaging over the family. By that I mean 1 over the size of the family. Summation E belong to the family. And I have a parameter big X. And this function that I just defined. Okay? Where f of x is a family of elliptic curves. Such that the conductor of E, well, let me say the conductor of E is about x. So for example, as Jordan was saying, I'm going to localize. So the conductor would go between x and 2x. I can say the conductor is up to x, it will not change things, but I'm going to say the conductor is about x. Okay, so the conjecture, and let me introduce it to. And actually, it's not only for a family of elliptic curve, but I wanted to write a precise family. Sometimes it's awkward to state things in general. Is that this limit, when I average this thing over my family, and okay, and now this is this thing that I keep saying, what actually goes to 0 now is the size of the family. Because I'm looking only at the low-lying 0. So I'm taking a bigger and a bigger and a bigger family, so I have more and more and more zeros. So this will go to the integral of f of x. And now I want to write the same kernel that I wrote before for the pair correlation. I want to write the scaling density. Of course, it's going to be a different function because that's a different statistics. So let me write this wg of x dx. Okay. And can you still see it? Because now I'm going to say what it's wg of x. So where wg of x, so it depends on the symmetry type of the family. me I'm a bit formal because there it looks like, oh yeah, no, that's right, I have a family of elliptic curve, I didn't tell you which family of elliptic curve. Though, when I'm going to list the possible scaling density coming with symmetry type, families of elliptic curve cannot all symmetry type, I'll explain that. So there's no universality. For the pair correlation, there was some universality. You would always get the same scaling density. You can even take pi, any automorphic form of GLM. So you can take anything you want, there's universality. Here there's a symmetry type. So let me give you the scaling density for the symmetry type. So there's going to be, again, unitary. So if you have unitary matrices. So there's going to be symplectic matrices. So SP. So in fact it's USP. I want them to be unitary. And then you can have type of orthogonal matrices. So I can have all orthogonal matrices. Let me write down and explain that. So this would be O for orthogonal. And now I can have SO odd or SO even. And SO odd will be 1 plus delta 0 of x plus sine of pi x over pi 2 pi x. And SO even will be 1. In fact, SO odd should be minus, I'm sorry. 1 plus. And it should be 2 pi x. I'm thinking about, so there's a 2. So the scaling density depends on the symmetry type of the family. So you can have those various scaling densities. So the scaling density, of course, always depends on the statistics. But here it also depends on the symmetry type of the family. So where is this conjecture coming from? Of course, it comes from the random matrix theory. Okay? I'm not going to write that, but suppose I was to say, okay, I take unitary random matrices or orthogonal random matrices, and I look at the one-level density, I can do that. And I take the limit as n goes to infinity, I would get those measures. Okay? So if I take n by n unitary matrices, and for those matrices I look at the one-level density, and I make the average over the size of all the matrices with the R measure, I'll let n goes to infinity, I would get here this circle. In that case, that would be a theorem. So would you like me to write that out, or it's okay? I can write explicitly. Okay. Now that's the question, and that's what I'm coming from. Okay, you can kind of, those matrices, for example, so if there's a 0 at, s equal 1, that's obviously an important feature of the family, it means one of the eigenvalue would be 1. And this is something you can see. For some of those, one of the eigenvalue would be 1. For some of those, so basically, if you know the root number, that's going to tell you the family. But one thing I want to say is that it's you can make things like try to determine the symmetry type, but you have to be careful because of the support of the Fourier transform can give to misleading results. That's exactly one of the things I want to say. Okay, and maybe I say those are the scaling density. For the same statistic, which is the one-level density, on the matrix. Okay, so let's say, I said I will not write it, but let's say I take G is equal to UN, okay, and I integrate over UN, what would be the one, maybe I write WF of U. I'm not writing what is WF of U, but WF of U, it means you would look, here you would look not at the low-lying 0, but at the low-lying eigenvalue. So I would have the same test function F, and I would integrate that over the space of unitary matrices with respect to the R measure, and then I would let n go to infinity. In that case, that would be a theorem. And I would get the integral over R of my test function F times what I get for the orthogonal family. So this conjecture comes from this theorem. This is always the idea. The statistic should match the statistic of the random matrices, but you need to take a limit because you need to make statistics, you need infinitely many things. So families of elliptic curve, you take more and more elliptic curve. Random matrices, you let the size of the random matrices go to infinity. And by the way, this thing is f at of 0 plus 1/2 f of 0. the right orthogonal? Actually, of course, yeah, because I'm dealing with an elliptic curve. Thank you very much. You're perfectly right, but I wanted to write both. That's my excuse. Yeah, and now I have U du because U is my matrix. I should have used A for my matrix also, maybe. Yeah, but U is my matrix. Yeah, you're perfectly right. It's saying if I'm taking unitary, of course, my scaling density is 1. But if I'm taking orthogonal and elliptic curve or orthogonal, my scaling density is that. And this is why I wanted to write that, because you'll see that in the theorem that I'm going to prove. Okay. So if I was to write, so remark. So the Fourier transform of O, SO odd, and SO even agree for U smaller than 1. Okay? I could write a Fourier transform, and for U smaller than 1, you cannot distinguish the Fourier transform. So what does it mean is, if you prove a result where the support of the Fourier transform is contained to -1, 1, Rachel was asking how do you determine the symmetry type? Well, you can say it's either U, it's SP, or one of the orthogonal, but you cannot determine which one it is. Okay, so let me take the first family of elliptic curve. A 2-parameter family of elliptic curve. And I'm going to take A, so I want the discriminant to be about X, the discriminant or the conductor. So, well, not the same thing, but let's say I want the discriminant to be about X, and I can deal with the difference with the discriminant of the conductor. So this is going to be like that. For this reason, such that the conductor of E is about X. Because the conductor is for Q plus 1. Left, right, up, down? This is right, by the way. Okay, but you're telling me left and you're pointing right. Okay, so you want it like that? Okay, yeah, my left or yeah, it's always confusing, huh? So is it good like that? So let me take a family of all elliptic curve, and you want to get a result to prove something about the one-level density of all elliptic curve. So what are we going to use? We're going to use the explicit formula. So the explicit formula, and we're going to see that in the case of L function over function field, or zeta function of curve over finite field, they're going to be very nice and very easy. That's one of the features. Because L function over function field are way, way easier. And in fact, in the project, the students are going to use that to compute the statistics. The explicit formula over number field are very, very nice also, but they're not as easy to prove. This is a completely different thing. So if you're me, for me, you're a classical analytic number theorist coming from the number field, it's always very surprising how some things can be simpler over function field. Not everything. So what are the explicit formula? They relate the sum over the zeros. Okay, my normalized 0 to, okay, let me write what you get. And you're going to think I'm kind of cheating because I'm writing the answer right away. But that's what the explicit formula gives you, and I'm going to explain to you why this is true. I'm just going to copy down and explain what's happening. E plus an error term, and my error term is log over log. Sorry, I should have. Okay, those are the explicit formula. F is my test function. I'm evaluating my test function over to 0. On the right-hand side, I get the Fourier transform at 0, 1/2 the value of my test function at 0, some sum over prime which involves, well, the most important thing it involves are the AP, the coefficient of the elliptic curve, and some error term. So where is that coming from? I don't have much time. This is also in the notes. But it is coming from to doing the integral on this line of this function. Okay, my test function is h, which is going to be a function of f, but if I want to have the correct normalization. And now I'll explain that to you in word why when you see that, you can conceive that, you know, with hard work you're going to get something like this formula. So gamma prime is a completed L function. So gamma prime has this square root of NE over 2 pi, the gamma function is the L. The gamma function, gamma prime over gamma, as you know, it never counts. I'm going to do the contour integral, moving contour, the gamma function goes in the error term. The square root of NE over 2 pi, that actually gives you the f at of 0. That's a trivial term that you can deal with. So in the explicit formula, okay, so what is the explicit formula? You compute this integral by moving contour. So you move contour up to 0. Okay? So what do you pick? As residue, you pick all the poles of this function, which are all the zeros of the Riemann zeta function. Because the gamma lambda prime over lambda has L prime over L inside it. Okay? So by Cauchy's theorem, by moving this integral, you get that. This is the sum of the residue. Okay, everything has to be normalized and you have to work. I just told you that's simple. So you apply Cauchy's theorem by moving this integral, you get that. And on the right-hand side is what I was telling you, evaluating this integral using the functional equation. So by evaluating this integral, maybe I can repeat that. Let me write it here, the gamma of s, and now I forgot my e. There's an elliptic curve. This is going to be square root of n over 2 pi to the s, gamma of s, L of s. And of course, the important thing is going to be this function. And if I write this function, this is going to be a sum over p, a sum over k. Yes? Oh yeah. I'm just throwing them on the side as I need them. Sorry. I'm very sorry. Let me copy that to make sure I don't make a mistake. Okay. I'm not going to write more. I'm going to explain from this. Okay. I think I have everything that I need now to explain. Okay, I want to explain this to the formulas. Actually, I'm going to change my sheet because I want to point at this thing. Okay, so when you do lambda prime over lambda, you're going to pick, well, this term. Can you see what I'm pointing or no? Okay. You're going to see this term, which gives you this term. The gamma term, as usual, doesn't give you anything. You can put it in the other term. And main thing is the L. So you will notice in the L, I have a sum over P and K. And this sum is for K is equal to 1. Okay? The sum over K equal to 1 is here. Primes matter. Powers of prime bigger than 2 never matters. That's something that, is usual. So K bigger or equal to 3 never matters. It goes in the error term. And K equal to 2 really matters, in fact, when you do the explicit formula. That's one other instance that squares of prime really matter, because for square of prime we get this. And this is not AP, because AP is alpha p plus alpha p bar squared. This is AP squared minus 2p. So for square of prime, the AP square, or the sim square is analytic, doesn't give you anything, and the minus 2p gives you this 1 half f of 0. This is what the explicit formula is. Okay, so now what you wanted to know, the sum over the zeros, you have explained it as something which is a sum over the coefficient of your curve. Now I'm going to average. So if you do the average, so then if I average the one level density, I'm going to just average this formula. Well, of course, the first two terms, let me write them, I'm going to add f out of the point 0 plus. Is it good? The right-hand side sheet? 1 half f at the point 0. And now I'm going to add the average plus 2 over log x. Summation p is smaller than x with the delta. I have a 2. What time I start at? 10 before, I think, huh? Okay, I have 2 7. Okay, so I'm writing that, and this is what you get when you average. So if you remember the f out of 0 plus 1 half of f of 0, I wrote it before. If you integrate the scaling density of the orthogonal group, you will get that. So the answer is there staring at you. So if you can manage the error term, it will tell you that, if you can manage the error term, show that this goes to 0 compared to that, you will get that as an answer. But if you remember before I wrote that, if you integrate, when somebody corrected me because I wrote, u in that O, if you integrate over O, the scaling density, you would get exactly that. You would get f out of the point 0 plus 1 half of 0. It would show elliptic curve. The one level density of elliptic curve is given by the correct kernel, and that's orthogonal symmetry, which is what we believe. Okay? The thing is, I have here this p to the delta, and this is provided the Fourier transform as support in minus delta. So that's why if you look at my previous formula, I have this Fourier transform and this infinite sum of prime sum is not a finite, it's not a sum which is chopped because I'm assuming something of the Fourier transform. So it's kind of one of those weird things that you will get a theorem. It's just a question of getting a theorem for the delta. So, and let me give you this. This was proven by Mathion. So, and I'm not sure I want to say this theorem. Yeah. So Mathion proved that for support of f hat is contained into, so the values are minus 7 half over 7. So you see exactly what happened. He managed to control the error term when the support of the Fourier transform is contained in that interval, which was, really a big thing, because the previous bound was a slightly larger support given by E Brown, and the previous bound was kind of something you had to beat for a very good reason. I'm going to explain that to you. And beating the bound of E Brown to get support in a slightly larger region, which Matt did, was really, really a big thing. And then you get, but the main term you already knew, you get the error term. And this confirms, I want to say this confirms O symmetries. Well, but also SO odd or SO even would work. Because the support of the Fourier transform is contained in -1, 1, by Cauchy-Reel's theorem, if you've integrated the f of x times the scaling density, it's the same thing as integrating the Fourier transform, and then you cannot distinguish. So this confirms O symmetry. Well, it would also confirm SO odd symmetry or SO even symmetry. But SO odd is for curves which always have phi of the functional equation equals -1. SO even phi of the functional equation equals +1. So clearly here it has to be orthogonal symmetry. But then in 2 seconds I'm going to give you an answer where you don't know the answer in advance, and you can make a mistake because of this limited support of the Fourier transform. This also implies, so a corollary of math words was that the average rank and that's one of the reasons why I wanted to give this formulation. It's going to be smaller than 1/2 plus 9 over 7, which is actually 24 over 14. So if you can prove something for the support of the Fourier transform of 2x to the delta, you get that the average analytic rank is smaller than 1/2 plus 1 over delta. Okay? That's why if you assume Katz and Sarnak, then you can prove it for all range of the test function, you get that the average analytic rank is smaller than 1/2. And at that point, it was, now of course, think about the average rank, even the average algebraic rank. We know a lot of things, thanks to some people which are actually in this room. Amazing result. But at that time, that was the first time that we can show that a positive proportion of the curve have rank 0 or 1, because the average analytic rank was smaller than 1. And also in that case, if you know that the average analytic rank is 0 or 1, you know that BSD is true for both curves. Going from analytic to algebraic in a way is less difficult than going from algebraic to analytic. So that was a big thing succeeding in proving that. But now, you know that this also proved as S-symmetry, the application to the rank is a corollary, but there's something that the support of the Fourier transform prevents you really from saying something more about the symmetry, and let me look at an example. So let's look at an example where the symmetry type is not clear in advance. I'm going to take a 1-parameter family of curves, which is a very nice family. Let me copy it to make sure I don't make any mistake. So before it was a 2-parameter family of elliptic curve, A and B vary. I'm going to take a 1-parameter family of elliptic curve, and let me write it correctly, x cubed plus t x squared. So it's really not a random family that I'm writing. Plus 1, sorry, not plus t, but it's plus 1. And I'm going to take t to be an integer. So this is a family which is due to Washington and Rizzo. It has a rank. Well, it was first studied by Washington, but Washington proved result only when the discriminant was curve-free. Rizzo completed the result. This family has rank 1 over q of t. And also also it has the fact that the root number, this is a very weird family, is -1 for all t in Z. It is possible to have such curve. But one of the things, for example, is this curve, according to there's some work of Elga, Carol Elga, who was this thesis, about can things like that should happen, or should the average of the root number should always be 0? If there's one place of multiplicative reduction, the average of the root number should be 0. But this curve actually has additive reduction everywhere. Okay? And it's a very special curve. It comes from Galois theory, actually. It comes from cubic extension, what is called the simplest cubic extension. And finding a curve like that, if you write a random curve, it's not going to be like that. If you write a random curve, the average root number is 0. So if you take this curve, yes. Q of t. Yeah. Yeah. No, okay. Yeah, it's an elliptic surface. So you look at over Q of t. It has rank 1. Okay? And then you look at all specialization. It's a one-parameter family, so you over Q of t, it gives you an elliptic curve, because there's y and x. And there it has rank 1. And now if you specialize the value of t, it gives you an elliptic curve over Q. That's what I mean. Okay, so if you look at this family, so Steve Miller, look at the one-level density for this family. Okay, so if you look at f of x, it's going to be the set of the curve ET in the Washington family. So I didn't tell you the formula for the conductor of the discriminant, but that's a polynomial of degree 4. So if I want to add conductor about x, I'm going to do it x to the 4. And it doesn't matter. It would be the same thing because you normalize anyway. So you look at the one-level density in this family. And you got for some limited support. And I think the support of the Fourier transform is -1/3. So what does it mean? This agrees with, and then you conclude that this agrees with, what should be the scaling density? Well, the scaling density, so f at 0 plus 1/2 of f0 is orthogonal. Well, it's also orthogonal even, it's also orthogonal odd. You know, why do I have 3/2? There's a force 0. Huh? There's a 0 over Q of t. So every specialization has a 0. So this thing should be understood as, you know, f of 0 plus f at of 0 plus 1/2 of f of 0. And this one is the force 0. And what's left agrees with any orthogonal under the sum. So because the support of the Fourier transform is limited, and so Steve Miller concludes that this should be, well, a Dirac function, which accounts for that, and then probably then SO odd. But because this agrees, because the sign of the functional equation is always -1. But in fact here, it's not clear what you should get, you know? And if you think about it, you know, in fact, when you pull out the 0, it's not clear you should get SO odd. I guess it's just a reflex to say if I have a family where the sign of the functional equation is always -1, I should get SO odd. But it agrees with a lot of things. And this is an example, and this is what Rachel was asking. How do you determine the symmetry type? Well, you prove result for the support of the Fourier transform large enough, but you cannot. So maybe another way to determine the symmetry type, and this is some result that I proved with Du Kian Yun, and Parks, and David. So what do you do if you cannot extend the support of the Fourier transform? Well, you assume more conjecture. Okay? So there's something which is now classical in the random matrix theory, which are called the ratio conjecture. So then, if you look at I'm going to take again the Washington family. So I didn't change my notation, you know. You notice that this is exactly the same left-hand side that was in Miller's theorem or Young's theorem, but, you know, in Young's theorem that was for all elliptic curves. Now in Miller's theorem, in this result, this is for the one-parameter family of Washington family. So, and when you use the ratio conjecture, what you get is not the Fourier transform, you get really the scaling density. And the scaling density that we get, what's that? So, which is, i.e., the scaling density agrees with it agrees with delta 0 x plus, if you remember, determine that, can we say, okay, in that case it should be S, so even we're assuming more. We're assuming another, it's a completely different technique of proof, okay? So we're assuming the ratio conjecture. It's kind of a, and the other thing, there's no way to say, oh, if I extend the support of the Fourier transform, what would I get? There's kind of no way to put those conjectures in the explicit formula, but there's a way to put those conjectures there. Okay, so that's an example where the technique to determine the symmetry type, well, it depends, you know, it can be limited. And in fact, it makes sense that this thing should be that plus SO even. So this kind of a general phenomenon that if I have a force point and I remove it, well, the rest should be like an elliptic curve with, you know, if I remove the force point and the rank was odd, well, the rank should be even for the rest of the elliptic curve. Okay, there's other way also to explain that. Okay, so why I'm explaining all that is to tell you what's happening for the situation over number field and to get you aware, first of all, of the explicit formula, because we're going to work over that over a function field, and also that what are we going to get over a function field for the support of the Fourier transform? And in fact, we're going to get the same thing if we don't take a Q limit. You don't extend the support of the Fourier transform. And the example that in the 10 minutes that I have left, let me concentrate on an example that actually we're going to do over function field. Yeah. In the 5 minutes that I have left, I'm very sorry. Let me look at another family. So here chi d is a Dirichlet character. So this is a family, and I'm going to take, so it's a quadratic Dirichlet character, I'm sorry. D is a fundamental discriminant, and I'm going to say D around X. And what I want to determine is the same thing, the one level density, and this is due to Sarnak and Uzbek. So let's do the one level density. I'm not defining things, but you can imagine that they're defined in exactly the same way. And maybe my family I will call D of X. So let me look at the one level density for this family of L functions. What is WF of D? I'm not going to write it. WF of D is I sum over all the zeros, F of those zeros. The normalization of my zero would be gamma log D over 2 pi. And my function will be a Schwartz function, which is to say it dies very fast. So I'm only looking at the first zero. So you want to look at the one level density for this family, and what we prove is that 1 minus final 2 pi x over 2 pi x dx when the support of f So, and then this means symplectic symmetry. Notice that for symplectic symmetries, you didn't need, any support will tell you. All the three orthogonal group are the same, symplectic or unitary you can distinguish. So this asymplectic symmetry as it should be. So why is it asymplectic symmetries? Because here the zeros are paired, by the way. So for each zero, so if I write my zero as 1/2 of I gamma, I have, if gamma is a zero, minus gamma is also a zero. So that's why you have symplectic symmetry in that. Okay, and then people wanted to extend that to the, so try to extend to the n level density. For the same family. So I'm not going to write you what is the n-level density, but you take a test function and you evaluate it at n0, and the test function dies very fast. Okay, that's another statistics. And this was done by Mike Rubenstein, actually, in his thesis. That if you compute for this family the n-level density, so that's going to tend, it's always as x goes to infinity. Here there's going to be a function of n variables. Okay? And I have this thing with, let me write the kernel for the n level density. The n level density, it will give you a function of one variable. There would be some kernel, which is a scaling density, and the kernel would be what it should be. Everything was good. So the only thing that people found which was not satisfying is that when the Fourier transform as support contained in the summation of the absolute value of the UI is moderate. Oh, sorry, that would be great. So this is not the result of Sarnak and Oslo-Snyder. Because the result of Sarnak and Oslo-Snyder would be the support is smaller than 2. So there was some partial work. This is what I don't want to finish late, so I'll talk more about that when I talk about function field. So try to extend Q. So there was some work by Gao, and then, which worked for n equal 3 and 4, and then for Miller, which worked for n equal, I think, 5 or 6. And actually, their work is not just they prove some cases. They managed to write this, okay, for all m. I mean, this is Gao, it was his thesis. He managed to write the n-level density for this family of L function for all m for a complicated expression. So maybe that's the last thing I wrote. So what Gao did, he managed to write as some crazy combinatorial expression, which I'm going to call AF, which takes more than one page just to write what it is. But there's always crazy combinatorics coming into that because, there's a question of, the diagonal term, the non-diagonal term, what you have to compute. But the thing is not this crazy combinatorial expression. You have to show that this was equal to the scaling density of your matrix group. And people were only able to do it for k sum n by n case, though the formula is valid for all m. And in the case of the last work of Miller, it's also with a lot of computer stuff. So this was solved now, and this is one of the things I wanted to talk about. So this was done for all n recently. This was proven. So this was proven, I mean, the result for the extended support that we think it should be for all m by Fontaine, Gershon, sorry, that's a 3, it's only 3 person, it's going to look like it's 4, but the middle name is 1 person. So using curves, hyperelliptic curve. I.e. the equidistribution theorem. And I want to put the big question mark here, exclamation mark. I don't know that word. Yeah. So in the rest of my lecture, I'm going to talk more about function fields, and it's going to be, they're very, very nice tools over function field, you can prove more, and this can serve you as an analogy, a lot of people said that things can be true over number field. But that's the first case where you can actually prove something over the function field and transfer it onto the number field. Okay? And I'm going to talk about that in the lecture. Sorry, 1 minute. Thank you.